morning, everybody, and thank you for welcoming to the West Midlands. I don't usually come down here. I like to see the hills and beautiful country, darts and tannic mills. That's a joke. Basically, my concept tonight is to bring to you an idea that the industry's changing for a start. No longer is the term darts and tannic mills acceptable. We all have problems recruiting people. And part of that reason is we've got this modern world, we've got to have an environment where people want to work and also it's safe, secure, and in the long term will meet the requirements of sustainability. So this particular paper is talk about that concept. So go with the first slide. Okay. Okay, sorry. You know, silica sand is basically 95% quartz, and it's the widest used medium to make castings in the world. Obviously, there's issues with the material. It's in recent years, and after long studies done in Europe, there's a big connection between silicosis and the silica crystal, clear quartz, has been deemed possibly a carcinogen, and because of that reason, the levels of airborne crystalline quartz, respirable quartz, have been brought down significantly. The UK at the moment is 0.1 milligram per meter cubed. And if you put it in Europe, it's 0.05 milligram, and the US is talking about 0.025. That's 25 micrograms. We probably get that level sat on the beach. Okay, so that's the level they're talking about. And that option we can do. But have to install significant PPE, and I'll make the certain things that we do now. The shot blasting process will have to be cleaner. The dust removed from shot blasting have to be better. The days of blowing molds out and all that will end. So the old restrictions we put on ourselves and how we operate with this medium crystalline silica. Next slide. Most sand is supplied, washed and dried, and it has at that point has low 0.5 at 63 micrograms. What happens to the thing when we get the silica sand? Well, if we knew, and this is worse in say countries like the UK. Sadly, UK silica is not one of the hardest in the world. It's a moderate hardness material. So pneumatic conveying it degrades. So that creates a fair amount of dust. Thermal shock. Silica, we all know, goes from alpha to beta quartz. That causes thermal shock on the sand. It causes the grains to crack and degrade. That creates dust. The mix of sand blowing out of mold creates dust. Knocking out of cast molds at the shakeout or knockout, you call it in the UK, basically that causes an issue with dust. The reclamation of foundry sand, the term is dry attrition. Most foundries in the UK who are not green sand are predominantly using mostly dry attrition. The process itself creates dust. It causes sand grains to smash against each other, and again that creates fine silica. The form repeated heating of sand in a system, you claim it, the more you heat it, the more it degrades thermally, you can do a thermal shock, and the transition from alpha to beta quartz, that itself will cause fractures of the sand grains. Generally, housekeeper, I go around the foundry, you've got dust on the girders, and you have dust, somebody knocks the building, the dust comes out. The foundry will have to be clean. There's no way you can operate at these levels we're talking about in the traditional way we operate the foundry industry. It's during all these operations that it's created. Foundries can use extraction processes, right, to minimize the dust. In the reclamation process, we use air separation to keep the efficiency of the dry attrition process. We use air separation through a fluidized bed. That itself is blowing off respirable quartz. We have to collect that in a bag house. If that system isn't properly controlled, then dust will enter the foundry. I'm sure as people in this room have seen their shakeout with dust coming out of it. That is going to be a no-no. At some point, it'll have to be completely enclosed. This is what we're facing. We're using silica. Next slide. Just tap the end key will do it. Yeah. This one there. Yeah. Ceramic sands produced around the world are predominantly mullite. Now, mullite is basically amorphous silica, and even the highest quality of these materials, the maximum crystalline silica in these, most are zero crystalline silica, but ceramic sands at maximum have 2% crystalline quartz in them. In the UK, present WL for a spiral crystalline silica, as I said, is 100 micrograms, 0.1 milligram per meter cubed. Whereas for an amorphous silica, it's 2,400. Now, I don't have to be a rocket scientist to explain that's 24 times. The respirable level of amorphous silica is 24 times the crystalline silica. That puts a bit of a different aspect on it. But I use these sands more aggregate. The amount of crystalline silica is virtually limited. If you use one certain types, you won't be using a crystalline source of silica in the foundry. That changes the options available to us. Cerebes are one option. They can be used across all the things like alpha set, phenolic urethane, no-bake, phenolic urethane cobalt. The whole binder systems work exactly the same. They have a benefit also they're round. The next slide. So here's some example. This is a company in the US. It's called Kimura. It's one of the biggest 3D printing foundries in the world. It prints 3D molds, production, as well as prototypes. Next slide, sir. These are what they found. You see here, total respirable dust concentration 200, respirable silica content 4.7 micrograms. So they're operating with a level of dust of 200 micrograms, which, if it was silica sand, would be over the UK limit and 4 times the US limit. Because they're using a non-crystalline sand, or virtually non-crystalline, they've got 4.7 micrograms of respirable crystal quartz. Next slide. And here's some example of the Bi 3D molds, Brittany Furan. Next slide, sir. So examples of being assembled. So this is not a small place. It's 3D printing. They make some quite big molds, 3D print. And next slide. So just mentioned from the Alpha Set foundry, and you see again in Korea the cristobalite or crystalline quartz. There was no detection whatsoever because the whole foundry was using a non-crystalline sand, using a ceramic sand. So there's no crystalline quartz detected. Next slide. Dust measurement of Cerebes versus silica. So your standard Cerebes system, conventional silica system, this with a lot of extraction still on, they were getting dust content of 1,316 micrograms above the threshold limit. When they came to using crystalline Cerebes in this case, there was no crystalline detected, and they were getting 2,000 micrograms of airborne, not amorphous dust, which was within the limit. Next slide, sir. So doing a quick comparison of the process, if we look at what our options are, if we take the replacement option of replacing the existing silica sand with the ceramic Cerebes, firstly, you can see there's a significant capital investment for either thermal reclamation or secondary nutrition. When I say secondary nutrition works. The problem the UK people's had with secondary nutrition is, again, because the sand is softer, when you put enough pressure on the secondary nutrition unit to actually make a successful high level of reclamation, it crushes the sand. You'll see later in the presentation, if you use a ceramic sand, the crush strength is 5, 6, 7 times that of silica. So therefore you can run the right level of pressure on the secondary nutrition unit to actually get a high level of reclamation. So it's not the unit that's affecting the performance of secondary nutrition, it's the softness of the sand. Right? That's a problem. So you can't get it to the pressures you really want to. So obviously investment in the nutrition process. Higher levels of reclamation of silica sand due to increased crush and thermal shock. The other benefit of a ceramic sand, it doesn't suffer thermal shock. So it doesn't degrade with the thermal cycling of the sand. Same in the people who's doing thermal reclamation on silica will say there's a loss because you're actually getting thermal degradation of the silica sand. If you run the ceramic sand, that degradation doesn't take place. The other big one, which we haven't talked about, if you've got dust, disposal of will not contain crystalline silica. If you're using a system based on silica and you're collecting all that dust, you have to get rid of it. And a lot of the waste sites, unless you can find beneficial reuse for it, don't want it because it's becoming a material that nobody wants. So that makes, again, harder to work within those parameters. You've obviously got an increased energy cost through the reclamation unit if you go for thermal, but that could be offset by using the energy for the waste heat for something else. So that's a negative. You got significantly improved casting quality. If we had our choice technically, and I said to people in this room, if there was no cost, would you use silica to make molds? You wouldn't. You'd use a medium that's much more suitable. The reason we use silica sand, because it's cheap and we throw it away. But from a technical stability point of view, if we could just make a casting how we'd like to make it, we'd probably use a ceramic sand or other medium because it's better. So the benefits of using CeraBeads is they're round, you get higher packing density, there's less thermal expansion, so effectively, in a lot of cases, you'll improve your dimensional accuracy of castings and you'll also improve the surface finish. In some cases, I'll show you later, as foundries now use the material in the world that's mostly in certain parts completely stop coating the molds, and these are steel foundries. Okay. So that's one benefit. In a lot of cases, you remove coatings, no crystalline at present, so no risk of future changes to legislation. Why I'm saying that, so you can spend a lot of cash, and then 3 years later, the government says, "Oh, sir, it's not 0.1 now; it's 0.025." Now, what do you do then? So it's a moving target. You can't predict in the future where this is going to go. And what they are saying, I know there's a long study being done in Europe about it may be cast like it eventually become like asbestos. You know, if it gets to that stage, what's the foundries going to do? So, and there's the negative of the high initial cost to replace the silicas, and obviously you have to buy a significantly higher expensive material and replace that. But once you replaced it, if you're running high levels of reclamation, like 97, 98%, then the top-up cost is much less. Okay, if we look at the other alternative route, which is called the arrestment route, so we continue where we're going and we go to operate through better extraction and arrestment. What do we have? Well, you've got capital investment for better extraction equipment. There's no payback for that. There's no improvement to casting surface finish. Basically, it's just going to collect more dust for you. Okay, so that's a cost with no payback. And you got increased energy and maintenance costs. So you get increased your extraction plants, whether it's your shot blasters and everything else, to keep those materials, the atmosphere clean, the shakeout, whatever. Again, there's no payback for it. In the case of AlphaSec, continuous of simple dry attrition resulting in continued rising costs of risk and disposal. Example, if we stay as we are in certain processes, we are going to get best 70% reclamation. You've got 30% of sand to get rid of. So you still have put this arrestment in, you develop the process, you've still got a waste stream, you've got to handle the 30% waste, which has to go somewhere. Now, if you get beneficial reuse, or good luck to you, but as it stands at the moment, a lot of sands, foundry sands, are going to get classed as special waste. Then the cost goes even higher. You've got to replace that with 30%. So you basically, you're looking at a non-finite resource. So you'll become more competitive for that resource called silica sand because we're throwing so much away. The increased requirement just to clean the foundry. Like I said, no blowing molds out, I'll have to stop, you have to vacuum them out. You're going to have to, vacuum the foundry, get clean. The days of, just dust being everywhere will not be acceptable. So a cleaning problem will have to be very high standard because the airborne requirements are so low. Workers have to wear PPE for the HSE doesn't like this. I'll give you an example. I was at Weir Foundry on a week or so, 2 weeks ago, and they've had to buy airstreams because the HSE began for, I think, John Witters, we've had a certain application to buy airstreams. Really, in an environment you wouldn't say by our foundry standards would be any issue. And we have had to spend over 100K on airstreams that the work operators have to wear. And this is a fairly clean, efficient foundry by what we understand. So the foundries are going to be put on very difficult times in the future where they got to wear by expensive PPE or conditions to allow their operators to work in it. And then at some point, if you really analyze it, somebody's going to sue somebody. That's going to be next, you know, so we get silicosis and sues a foundry for silicosis or whatever. And then what happens to the insurance situation with the insurance? You know, so the whole risks are there. We have to manage them if we stay with it. Okay. So difficult recruiting, like I said before, as people want cleaner environments, it makes dirty environments make it difficult for people to recruit. The benefits of harassment, we got low cost of aggregate. I put there like a yellow one. There's no guarantee, still a risk that threshold limits will not change, will not get lower. We don't know that. So the problem with the right-hand option, just increase investment, is from a business planning option. The future is, it's not dependable, you don't know. So how do you attract investment to an environment where there's no stability or potential risks in the future you can't identify? So that's the comparisons having a disadvantage. So yes, you can solve it on the investment side, but there's disadvantages. The advantage is low cost of the aggregate when you analyze it. Go next slide, sir. So technical advantages of Cerebees, as I've said, they are low thermal expansions. In some cases, it omits the needs for sand additives. If you're in internal cores, so coal box, you'll need anti-vein materials. You don't need them with Cerebees. So you got reduced vein and metal penetration because of the low thermal expansion, improved diameter capability. You've got higher core strengths because they're round. They have a lower resin demand. It's the same density as silica, but the resin demand is slightly less because of higher core strengths. Packing density is improved because they're round again. You'll get a much higher packing density. You may, in some cases, I'll show you in a second, that you can remove coatings, better all surface finishing, and high thermal stability. No need for special sand to prevent fusion and burnout. So in some cases, people are using chromite sand, or you know, they face them all with chromite, they face them all with zircon to stop burning. That option is resolved. You don't have that risk. So you're not using a sand that then ends up in the system being dumped like chromite. And I'll say now about chromite, I'm not saying chromium's a bad thing, but there's rumours coming around about hexavalent chromium with chromite. So, you know, it's not there. There's talk about it. I hear it here and there. I've never seen it written, but I've heard in Germany people mention, what about hexavalent chromium? So I don't know where that's going to go. So next slide, sir. Here's an example. It shows you the crushing. What they've done is recycle the crushing ratio of the different sands, and you can see the Cerebees has the best performance on a loss of density, loss of material through crush. So they measure how much material degrade, how much dust comes off. You can see the Cerebees is faster, but the worst is silica, chromite, zircon, than Cerebees. So Cerebees give a significant high resistance to crushing. So when using secondary attrition, that's a good property. Next slide, sir. So here's a process set up about primary and secondary attrition. So conventional primary attrition, you can see the simple process. In a secondary attrition, there's after the original shakeout, the primary thing goes into a secondary attrition unit to remove a hexagonal binder. This particular process in Korea attained a 97% reclamation on a mechanical process. This next slide, sir. So the significant is a example, the amount of new sand tons per month, 56, total mixed ton was nearly 2,000, new sand per se was 2.8, so 97.2% reclamation. That's actual data from the foundry. Next slide, sir. You can see the casting, it's actually that's a massive steel casting produced in Cerebees. So the whole foundry operates in Cerebees, it does not use silica, and they reclaim. And there's the crystalline, you see the what is it, the level of the For the normal operation, conventional system, they're getting 1.31, so 100, so 1300 micrograms or 1.31, 0.113 milligrams per meter cube. So that's over the limit for crystalline quartz. It's within the limit for amorphous quartz. Next slide, sir. This is foundry produces. This is basic data on the foundry. It produces pumps for the mine industry. It's in Florida, and basically they've switched their 2 foundries over to Cerebes. They basically is the example. That's the process to use, and they're putting in basically they use thermal reclamation, and they've eliminated the total requirement on crystalline silica, and they reduce the amount of zircon used. And in this case, the foundry doesn't have to, as in most cases, to stop painting them all. They still paint certain castings, and they're pouring chrome irons and alloy steel. Next slide. Just to show for the aluminium guys here. I can't tell you it's found in the US because it's part to do with Tesla, but basically the foundry is producing core assembly system for aluminium, and it's all Cerebes, the whole foundry, which goes into low pressure die casting. So the cores, if you're a foundry who's an aluminium foundry using shell or conventional silica, and you're thermally reclaiming, you don't really need silica sand. If you're claiming to high levels, why use silica? You don't need to. You're recycling it. Why bother using something what you don't really? The reason we use silica is we throw it away. It's cheap. For recycling it, we don't need to use it. Next, final slide here. So that's a basic summation of what I'm talking about. It's to give you a concept of what's available, what can be done, other than the simple things, put more extraction in. We can make found. There are founds. When I was in India at IFEX, there was a foundry being built, a brand new foundry to make duplex stainless steel pumps. Is building the Cerebes foundry. They're starting fresh with Cerebes because they don't want they want to be sustainable. Their customers demand that they're sustainable. Any questions?
What would you say the UK Cerebes do the UK think they use?
Sadly, in the UK, it's quite low. You know, and it's really stepping out of the comfort zone. You know, it's just take if I take just talking about sustainability. Forget Cerebes. Just talk about being sustainable, right? Completely recycling your product. Sadly, in the UK, that hasn't taken off, and I think because we look at net cost, not purchase. We spend too much focus on how much something costs to buy rather than the costs of what I do know, and I may have wrong. Richard Heath will tell you this. A lot of the founders have been visited, and they've got, we've got to do something, and what I'm offering here is instead of say, okay, put in a 250,000 CFM extraction plant, look at another alternative that can give you a much more, when you've done it, a more productive foundry. There's something back for the money you invest. Any other questions? Yes, sir.
You mentioned, sorry, you have to ask the question with the microphone for those online.
Okay. You mentioned differences in silica sands in like condition and quality, like you said, the English one's sort of middling hardness and things like that. Do this sand have the similar issues as it's?
You've got to wait for the microphone to answer.
Now, the reason why it's manufactured, it's basically a manufactured sand. I mean, Cerebes first came on the market probably after selling in the US in '92. And that was, but it actually started selling. They started selling in the US as a mainly for making cores out of, for things like hydraulic valves, that sort of application. It's only in the recent, well, obviously, in countries like Korea and Japan that had no indigenous silica sand or very good silica sand, that's why these products were developed in those parts of the world, because they effectively had to crush rocks to make sand. They did not have any deposits, so they quickly realized that from a beneficial point of view, just to make a synthetic sand. I think it was the advent of the silica health risks in the US especially, but also in Germany, people starting questioning, why am I using this material? So it's become more of a recent concept of high levels of reclamation and using a manufactured sand like Cerebeads, because if you have a higher level of reclamation and it doesn't degrade, why not use it? Because there's other technical advantages from it. Any other questions?
Yeah, it was just a question about, if you transferred over from one system to another, what do you do with the existing system? What's the cleaning techniques required on the existing hardware and plant?
Well, obviously, the main thing would be to vacuum all your system out or clean it out, like a proper clean down. You'd have to, if you got bag houses, they would naturally be cleaned anyway. What you'd have to be is, unlike today, where you may chuck the castings outside and let the sand just disappear, you'd be a little bit more focused on, decoring and clean the casting down. I think one other thing is it does fall off. It doesn't fuse to the casting, so in actual fact, castings entering the shot blaster will have very less sand attached to them. But so overall, you'd have to clean the foundry down. That's all you'd have to do, and dispose of all that. You'd have to use your sand, obviously, and the big capital outlay is initial purchase if you got the reclamation level. Yeah.
Who are the main suppliers of the ceramic sand?
Of the pure mullite ones, that is predominantly only it's as we sell. If you go down the bauxite sand route, there's 10% crystalline in them. So the only one that's completely crystalline free is the Cerebead. The bauxite naturally contains about 10%. So the other suppliers, there's other suppliers like, Minelco's, also names of people that do supply ceramic sands being bauxite. The basic people get confused. There's two basic ceramic sands outside of chromite and zircon. There's bauxite and the Cerebeads. They're the two main ones. Okay, there's several suppliers of bauxite around the world. There's China, there's US. I don't know if the European one, I don't know. But for the zero crystalline quartz, the Cerebeads is the only one.
Any more questions?
Well, from one question online was where are the Cerebeads produced?
At present, they're produced in Japan, and thankfully we have a free trade agreement with Japan, so we don't pay tax on bringing them to the country. Yeah, they're produced in Japan, but the distribute out Europe, that comes into Europe, it's distributed around Europe. If it's I've been non-selling my own product. If it's a bauxite sand, the source is China. There's one in Texas. There's one in Brazil, but I think the Brazilian one has a high iron oxide content, I think, if I'm right. So there's none originating in the UK. I don't think there's any in Europe. Actually, I'm not sure about the bauxite. They may be in Europe. But so when somebody like Minelco says they're selling you bauxite, it's not coming from Europe. It's from China. China's the biggest producer of ceramic sands in the world. But the Cerebeads, which have been around since '92, are from Japan. They're a Japanese product.
Any more questions? Are you going to give us an idea of cost?
Typically with these products, the arrangement that we have with the manufacturers, we stock some of this and buying the odd one and the 2 tons, you're looking at around £1,400–1,500 a ton for this material. If you wanted to fill a system, there's a fair bit lower price you can get. We can probably get about 30% lower than that.
Some foundries are using chromite as a thing, and they put chromite separators in. And again, the problem is they work quite well. So the cost of not using, I'm not having to use a facing type material on, and then the option of the secondary attrition process performing better than it does on normal silica sand. So put that into your thought process.
Yeah, so I can see that there's an initial higher cost, but then because you're reclaiming 97% or more, then over time it could become economical and effective, but environmentally it is better.
The other thing is to get to some foundries to get to the stereosilicon, to get to the levels, they have to invest these significant amounts of investment. And the big thing about it, it's a lot of money and maintenance costs you're not getting paid back for. You're not getting up for it, you know? And like I said, the other issue is what are you going to do with all this dust you collect? Who wants it? And the final thing I'm pushing, whether it's Cerebes or any process, if the foundries don't start reducing, a friend of mine works for Suez, right? And he's telling me that by 25, 26, councils will no longer dispose of, we'll call it household waste, whatever you want to call it, into landfill sites. So landfill sites will close, and the only sites that will be open will be for industrial waste. The problem is that means that waste may start getting classified as hazardous. And if it does, you're talking significant amounts of money to get rid of waste foundry sand, you know, which could be, unless you could find a beneficial reuse for it. And then there's the other thing from your arrestment plants. You got to find, you know, if you take the material next to the shot blast, the stuff that comes out of the shot blast is really bad, you know, from a point of view of respiratory damage. What landfill sites are people going to want this material? They're not going to want it because it's a hazard to them, you know? So that's another part to put into the equation. I'm not talking about doing this tomorrow. I'm talking yourselves, as you're planning your businesses, looking forward, what route do we take? That's
I noticed on one of your slides you said silica could be banned like asbestos. That's quite a thing to think about in our industry. You know, God knows what's going to happen. So I think this technology people have to become aware of. There has to be alternatives. There has to be a plan B.
final thing. I have a friend in the States, right, who buys an inorganic binder. Maybe he tells me, I'll tell him he can't be competitive. His sales every year grow because the company buying the components of him had been driven by their own governments and then they're being green. So they say to him, you've got a sustainable foundry. Well, he has one. He doesn't throw anything away. Now, the point being is, it's not just about what we want. Some of our customers will start demanding that we become more sustainable ourselves to supply them, because they have to tick a box and say, look, Mr. Governor, look, wonderful world, how green I am, right? The car companies are going to be the worst of this. So we have to accept that. And what I'm offering is a concept in your mind that you can build a foundry that looks or really clean, that will meet these conditions. Plus, you'll find it easy to recruit clean environment for them to work in.
Okay, questions? I'd like to call on Colin just to give the vote of thanks.
Thank you. So our thanks to Andrew for travelling down to see us tonight and delivering a presentation which I think we can all agree was full of technical content and relative to the industry that we work in for sustainability. And this is something that I'd like to support further at the National Foundry Training Centre. Our thanks to John Winters for sponsoring the buffet tonight and for covering the bar charges. I was kind. Can I ask you all to show your appreciation in the usual manner, please? Good job, Andrew. Good job.
Yeah, you beat me there. I was going to also thank Adam for sponsoring tonight and also setting up the bar. That was very kind of you. Thank you very much. There's a few little notices. This is an interesting